When calculating with lines or planes, it is often convenient to describe them by their parameterizations. For a line, you need just one parameter, and for a plane, just two. Suppose we have a line L in R3. Line L goes through the origin and has the direction of vector u. We can simplify the figure by leaving out the x's. The coordinates of vectors ending on line L can be described as t times 2, 1, 1, where parameter t may have any real value. If parameter t equals 1, you get vector u. If t equals a half, vector x becomes the half of vector u. If t equals 0, you get the origin. If t may be any real number, the endpoints of this set of vectors x describe the whole line L. Now a line in R3 not through the origin. Line M has direction u, but goes through P with coordinates -1, 1, 1. First define vector P as the vector from the origin to point P. A parametric vector form of line M is x equals P plus t times u. If t equals 0, the endpoint of vector x corresponds to point P. If t equals 1, x is the sum of vector p and u, which points to a point on line M. Each point on M corresponds to exactly one value of t. In this parametric vector form for line M, p is called the position vector, and another name for the position vector is support vector. Vector u is called the direction vector. The parameterization of a line is not unique. This parameterization describes the same line because the direction vectors are parallel. You can use mu is a half t. Take t equal to a half and you see that point Q lies on line M. So for the parameterization of line M, instead of vector p, we can also use vector OQ as a position vector. That gives another parameterization for M. You could even introduce a second parameter in this way. The set of x's still gives the same line because the two direction vectors are parallel. Do we want to use this parameterization? No. Better use the simplest form with just one parameter t and without parameter s. Only then does each value of t correspond to one point on the line, and each point on the line corresponds to just one value of t. To describe a plane through the origin, we need two different direction vectors. In this case, vectors u1 and u2. We use two parameters, for example, t and s. Each x in the plane can be expressed as t times u1 plus s times u2. In this graph, by varying t, you can go to the back or to the front in the plane along direction u1. And by varying parameter s, you can move in the left-right direction of vector u2. For a plane not through the origin, such as this plane w, you have to add a position vector. The position vector can be a vector to any point in the plane. Starting in point P, with the direction vectors, you can then move in the two directions of the plane. A plane is uniquely determined by two directions and one point. You recognize these three elements in the parameterizations. We have been drawing in R3, but you can generalize parameterization to higher dimensional spaces. For example, consider this as h of vectors x in R5. Because of the one parameter t, h is a line, with p as a support vector and u as a direction vector. And even though you cannot draw R5, you can still make a sketch of the situation. In this video, you have seen how you can write lines and planes in parametric vector form. For a line, you need just one parameter, one direction vector and a point. For the parameterization of a plane, you need two parameters, two direction vectors and a point.